Okay, hi Ani.
Hi Janakiraman.
So welcome back. And so today I just wanted to look at this concept of how one would measure a resistance. Okay, so I have here with me voltmeter, as you can see. Okay, and you can see that I can move it. I'm making the pointer point to the ohm meter, right? So it's going to measure resistance. Okay, so if I measure this value, okay, I get some number, okay, 46.6, the unit is ohms. Okay, so I just wanted to ask you, how do you think this is making a measurement?
Okay, see, most likely my guess is that it must be doing something, it must be using some electrical quantity to extract out the resistance. Right? And I also know that the resistance dissipates power in the form of heat.
Okay.
But you are not checking anything on heat, you are just making an electrical connection.
Exactly.
It cannot find out how much power is being dissipated as heat.
Heat,
so it cannot be power. My guess would be some voltage and current.
Voltage and current, okay. So you're saying you apply some voltage, right? And then you're trying to measure what the current is.
What the current is.
Okay, so so here, of course, the ohm meter does not know what network is. It's actually a black box.
It's actually a black box.
Black box, right?
That's right.
So maybe if we can draw a black box and then we can discuss, right? So we have a black box here.
And all I have coming out is two wires?
Two wires.
That's right.
Okay.
Okay.
So what?
So I can have all kinds of resistors.
Something happening, right?
Yeah. Something happening inside.
Okay. And you're saying that this voltmeter is actually applying some sort of a voltage?
Yes.
Okay.
Some sort of a voltage.
And this is like a DC voltage or?
Well, for a resistor, it may not matter.
It may not matter.
It may not matter.
Okay.
Because we know that it's linear.
Correct. Exactly.
Right. So maybe it doesn't matter, but obviously DC is easier.
Easier, right? So okay, for the purpose of this discussion, let's assume it applies a DC voltage, right? And you're saying it is able to measure the current that is going into that circuit.
That's correct. I'll call it some IDC.
IDC, right?
Yes.
So therefore, you're saying the equivalent resistance is given by?
So across these terminals that I've pulled out, I have some equivalent resistance. I'm going to call that R equivalent.
Okay.
This multimeter, when placed in ohmmeter mode, seems to be measuring across those two terminals whatever resistance is presented by this black box.
Correct.
Right? By applying VDC and IDC.
IDC.
And in fact, through a single measurement, it seems like you just connected it and it gave you the value.
I got just one measurement.
Right?
Exactly.
Right? In fact, in your case, let's maybe consider the simplest case.
Okay.
You just took one resistor. And took, right? So you looked at this case where you just, you just took one resistor.
Yeah.
Some resistor, unknown resistance R.
Yeah.
And you connected through a wire, right? And we said that it is applying some VDC.
Yeah.
Right? And it is measuring IDC.
Okay.
Okay. Well, I think I can see clearly that for this network, because the minute I make the electrical connection, I also already know that this resistor obeys Ohm's law.
Yes.
So I know that this has to be true.
VD. Oh, okay. So
VDC.
therefore, you're saying R is just VDC by IDC.
That's right.
And therefore, it's
In fact, it looks like I can just make one single measurement.
Okay.
And do it because, well, let's see if that is true, right?
Yes.
That's interesting. Now I'll go to the next page.
Yes.
Right? Because it seems to be giving the value immediately, right?
Yeah.
So let us see. I'm going to draw the VI characteristics
of a resistor.
Okay. Okay. So what I'll do, let me move this a little bit down.
Okay.
Okay. So we know that the VI characteristics of a resistor actually pass through the origin and occupies only the first and third quadrants.
Right.
Because we know that it is a passive element, it only dissipates power.
Right.
And it's a straight line passing through the origin. So the equation, if I were to imagine x and y coordinates, it's a straight line. It seems to be of this form.
Y equal to mx.
Correct. Mx, right? We know that the general form is y equals mx plus c.
Yeah.
But now in this case it passes through the origin, so c is 0.
Yeah.
So it's y equals mx.
Correct.
In fact, that is, this m is just the slope.
Yeah.
And in our case, we have v equals r times I.
Yes.
So that is, that slope m is the resistance.
Is the resistance.
It's a straight line.
Yes.
The slope is the same whether independent of where you measure it.
Correct.
Right? So I think it makes sense that whether I measure the slope here or here or here, it doesn't matter. I can even apply a negative voltage
and get a negative current.
Right. Find out take the ratio of the two.
Okay. Right.
Right? So it seems like a single measurement is enough.
Okay. So we don't know. So you're saying that this guy could be measuring it using any voltage and measuring the corresponding current. We don't know what the voltage is.
That's right.
But they will all give you the same answer.
It will all give you the same answer.
Okay.
But it has to be a resistor.
It has to be a resistor. Okay. Now, should it just be one resistor?
That may not be true because we have seen in class, right? We have seen that if you put two resistors in series, we have seen that there is an equivalent resistance. Purely for that simple network, we have solved KVL, KCL, and seen that it presents a resistive impedance also. Right? We talked about linearity of a network, and where we talked about saying that if you actually had a resistive network, it will still be linear.
So, should that be just one resistance in there, or can it be like a complex network of resistors?
Well, I'm pretty sure that it will be valid even if you have a complex network of resistors. But maybe we should find out.
Right.
We should take a look.
Of course, yeah. So can we just consider like a more complex network now? Let's say there are like maybe two resistors in series.
Let's do that. So maybe you want to consider a black box which has two resistors, right? Maybe R1 and R2.
R2, exactly.
That's what you're thinking of?
Yeah.
Let's do that. Let's do that. So this is my black box, right? So I will take out this. This is my black box.
Yeah.
Right?
Yes.
Okay, let's do that.
Okay.
So what I'll do is I'm going to see whether a single measurement will give me a resistance.
Yes.
Correct?
Yeah.
So let's do that. So what I'll do, I'm assuming that it's a DC voltage.
Yeah.
And you have asked me to put two resistors in series.
Yes.
So R1, R2, and let's assume that this is some voltage VDC.
Yeah.
Okay. Well, we can solve this using KCL, KVL.
Yeah.
Right? In this case, KVL makes sense.
Yes.
Because we have a single loop.
Right.
There are no currents to distribute.
Right.
So what I'm going to say is that there is a single current. I'll call that IDC.
Yeah.
And through Ohm's law for the individual resistors, I know that this voltage is R1 times IDC.
Yeah.
The same current flows through R1 and R2. So this voltage across R2 is R2 times IDC.
Yeah.
Now I can apply KVL.
Yes.
Okay. What I'm going to do, I'm going to start from here.
Yes.
I'm going to go up clockwise and come back and end at this point again.
Yes, absolutely.
So I'm going to start. I have a potential increase.
Yes.
So I'll write a potential increase as minus VDC.
Yeah.
And then a potential drop as positive.
Yeah.
So plus R1 times IDC.
Yeah.
Plus R2 times IDC. These are the two potential drops.
Yes.
I have come back to the same point.
So it is equal to 0.
It is equal to 0.
Absolutely.
Okay. So now this tells me that VDC is equal to R1 plus R2 times IDC.
Absolutely.
Interesting.
Right. So therefore, again, the multimeter, all it has to do is do VDC by IDC, and you get the equivalent resistance of that network.
That's right. Because if I were to plot this, this also seems to be a straight line.
Absolutely.
Right?
Yes.
That is why it seems like even for two resistors placed in series, this seems to be valid.
Yes.
Because I I took two resistors R1, R2. If I used one VDC and then maybe I increased it, IDC would also increase. Maybe I double VDC, IDC would double. And so on.
Yeah. And for any voltage, you'll get a corresponding current.
Correct. So maybe I'll write it.
Yeah.
Correct. So I'll write it like this directly.
Yes.
VDC by IDC is R1 plus R2. In fact, this is the equivalent resistance we have been wanting.
Yes.
For this case.
So equivalent resistance is as if there were only one resistor, right? The VI characteristics wouldn't change.
That's correct.
Right?
That's correct.
Okay. So can we make this a little more complex? If I had R1, R2 and R3 in parallel with each other. Right? Can we just
in parallel with each other?
Yes. R2 and R3 in parallel with each other.
Maybe let's start with, that I don't know how to handle.
Okay.
Maybe let's start with two resistors in parallel first.
Okay, let's start with R1
let's start with a simple case.
Yes, I agree.
So maybe we'll start with something like this.
Yes.
This is the simpler case. So maybe we'll start with this. So I want to find out if I have R1 and R2 in parallel like this.
Correct.
And I want to find out whether this will also give me a linear curve passing through the origin. Right? So I'll do the same method, which is to apply a DC voltage.
Yeah.
Okay.
Okay.
I'm going to call, it's going to draw some current. I'll need to find out what that is.
Yes.
But now I have a problem. These two resistors don't have the same current.
Yes. So the currents are going to be like I1 and I2.
I1 and I2. Okay. I'll call this I1.
And I2. And by KCL, IDC should be equal to I1 plus I2.
Right. So I'm going to do KCL here.
Yes.
Okay. So I know that IDC is equal to I1 plus
I2.
I2.
Okay.
And now I can do KVL as well.
You can do KVL. Yes.
Right?
So you have how many loops here?
I have two loops here.
Okay.
So I have one here. I'm going to choose the independent loops.
Yes.
So I'll choose these two loops.
Okay.
So loop 1 and loop 2.
Yeah.
Okay. So if I were to do KVL around loop 1, I know that I'm going to again start from here.
Okay.
Go clockwise and come back.
Come back.
I'll follow that rule.
Yes.
Easy. So this is KCL.
Yeah.
And I'll call it KVL number 1.
Yes.
Will give me, I'll get a minus VDC.
Yeah.
Plus, and now the drop across R1 is basically R1 I1.
R1 into I1. Yes.
Okay. So plus R1 I1.
I1
is 0.
0. Yes.
Now from this I can actually find out what I1 is.
Yes.
Right? I1
VDC
by
R1. Yeah.
Okay. And now loop 2, I am going to start with, I have a drop here. So I have a potential increase. So KVL number 2 tells me that minus I1 R1.
Okay. So maybe in red, can you just mark that second loop?
Yes. So that is that second loop, which is this guy here. This is the loop I'm doing. I'm going to start from here, go around the loop and come back to this point.
Yes.
Okay. So what I'm going to do is, I didn't choose red, I chose a different color.
Yeah, sure.
Okay. Minus I1 R1 plus I2 R2, which is the voltage drop across R2.
Yeah.
And now I'm back at the starting point, which was this.
So that is equal to 0.
That is equal to 0.
Right. Okay.
Now I can already see that I1 R1 seems to be equal to I2 R2. The voltage drop across the two resistors seems to be equal.
Yes.
And actually that makes sense because I am taking the same 2 points.
Exactly.
We know that the potential difference between 2 points, right, is unique. Right?
Yeah.
You might have multiple paths, but in steady state, we know that you can take each path. In fact, that's how we formed KVL.
Exactly.
We said there is a unique potential difference between any 2 points. You can go through multiple paths and create KVL.
Yes.
Right? So this makes sense.
So the other way to look at this is, there's the third loop, which is starting from VDC.
Absolutely. Yes.
That goes through R2.
Yes. Correct.
Right?
Correct. So I could have chosen, maybe I'll show it like this. I could have chosen this loop as well. And
you come back to the same point.
That's right.
So you can choose any 2 of the 3.
That's right. In fact, the circuit analysis people actually make a distinction. They call each of these individual loops a mesh.
Okay.
And the overall one, they can also be called loops, but the overall one is always a loop, it's not a mesh.
Okay.
Right?
Okay.
So the circuit analysis people, the circuit theory people make a distinction.
Make a distinction.
So when you go when you go around and come back to the same point, which traverses multiple meshes, then this is called a loop. It can never be called a mesh.
Okay. Okay. Right. So that's just a terminology.
Just terminology, just an aside for the students.
Aside. Okay. So you're saying, okay, so therefore if you go by the third loop, VDC will be equal to I2 R2.
I'll write that here, KVL number 3.
Yeah.
It tells me that minus VDC plus I2, I'll follow the same convention.
Yes.
I think I have done R2 I2 and I2 R2 in some cases.
Yeah.
I'll just follow something. That's okay. I think people will understand.
R2
I2 R2 is equal to 0.
So therefore I2 is now
VDC by R2.
R2. Okay. So so what is the equivalent resistance now?
So to find out the equivalent resistance, I need to find out VDC.
So it is VDC by IDC. Right?
That's right.
That is the equivalent resistance. The current entering the black box.
Correct.
Okay.
So that's right. So what I will do, I will go to the next page.
Yeah.
So IDC, I will now use the KVL.
Yeah.
So this was I1 plus I2.
KCL. Yeah.
Sorry, KCL.
Yes. Yeah.
I'll use KCL. We actually wrote it down here.
Yes.
The KCL equation. I'm going to rewrite that on the next page. And we know I1 is nothing but VDC by R1. And I2 was VDC by R2.
Right? Excellent.
Now we said that R equivalent is VDC by IDC. We somehow need to get that from this equation.
Yes.
All I need to do is
get IDC down,
and I need to somehow take this up. So maybe what I will do, I'll write it like this: 1 by R1 plus 1 by R2. I'll make it a little bit like this.
Yes.
So now I bring in IDC to the right hand side, denominator, and I need to take this to the other side.
To the denominator there.
Right. Okay. So this is nothing but 1 over
1 by R1 plus 1 over R2. So in effect we can say 1 by R equivalent is equal to 1 over R1 plus 1 over R2.
Perfect. That's a very common way of writing this because it's easier.
It's in parallel, right?
Correct.
Okay, great. So essentially all we have to do is find the current entering the black box.
That's correct.
Right? And V by I will give you the equivalent resistance.
That's right.
Right? And so question is, can this network have capacitors? Now what happens if I put like a R and C in parallel? I mean, should this be only a resistive network? Where can I apply this?
So I can already see that if you put any capacitors in the circuit, it's going to cause trouble.
It's going to cause trouble.
It's going to cause trouble because first of all, if you put a capacitor, I know that I'll have to solve differential equations.
Okay.
I cannot solve, simple set of linear equations. That causes trouble.
Okay.
But actually there's a bigger problem.
Yeah.
I remember that if you have capacitors, the capacitor voltage, because it's differentially related, so maybe we can write it down here.
Yeah.
So I remember that we talked about when you have a capacitor, if there is a voltage Vc, this is the capacitor C, and there is a current IC, we know that the relationship is IC is C dVc by dt. Now, there is a current through the capacitor only if the voltage is changing.
Changing with time.
Time.
So there's no, if you have a DC.
Yes, a DC is a constant.
Changing, right?
Correct.
Okay.
And in fact, that tells me if I give a constant voltage, the capacitor current is 0.
Right? So you will get, you could potentially get a resistance of 0 from this meter.
A resistance of infinity.
Because
current is 0, it's an open circuit.
Exactly.
So what I will get, I will just get, so suppose I were to try to measure the resistance in this fashion for a capacitor, what I would do is I would connect a VDC and try to measure the IDC. And
IDC is 0.
IDC is 0. So the R equivalent, imagine I took a capacitor and measured it with your ohmmeter,
you will get
I will basically get whatever VDC I apply, I'll get 0.
0.
So this will be
infinite.
It looks like an open circuit.
Right. So I think the only caution here is whatever we are going to talk about can be applied only if you know that the black box has resistors and nothing else.
That's correct.
Right?
That's correct.
Okay.
So we are going to deal with circuits that contain only resistors.
Only resistors.
That's
okay. And I think another noteworthy point is there are multiple loops, okay, in this thing, because as a student when I first started solving circuit problems, right, the real confusion was which loop should I take? Are they all the same, or will they give me different results? So if you can go back one page, right, you had like 3 loops. Now you could solve it with I1 R1 equal to I2 R2 also, right? It's just that it's more complicated, right? The KVL 1 and 3 were easier to deal with.
That's absolutely right. That's absolutely right.
It doesn't matter in a resistive network problem and finding equivalent resistance, there will be many loops that the student should be aware of.
That's correct.
But if you are trying to solve for certain number of unknowns and only that many loops you need to take, and hopefully in the next couple of discussions we should be able to give some insight into how to choose these loops, right?
Absolutely.
Which one is easier to work with than others and so on.
Absolutely.
Right?
In fact, one important thing to note is that you should choose loops that are independent.
That
needs to be independent.
Okay.
Because there is some dependence. If you, for example, have 3 meshes,
yeah,
you can't. So imagine. So let's take an example.
Yeah.
So what I will do, I will take that original mesh, but I'm going to add a third mesh.
Okay.
I'm sorry.
Okay.
So suppose I added 3 resistors in parallel.
Okay.
And now I know that there are 3 variables.
Yes.
I need 3 equations to solve for them.
And the 3 variables are the 3 currents.
Are the 3 currents.
Okay.
Right? I1, I2 and I3.
I3.
Now I cannot choose my. So suppose I choose this as mesh 1.
Yeah.
And I choose this as mesh 2.
Yeah.
They will give me equations relating to I1 and I2.
Yes.
I cannot choose my third loop as this.
Because it does not involve I3.
It does not involve I3 at all.
Ah.
So I need to make sure that the number of loops and the loops that I choose have some independent variables associated with the loops that I choose.
Right.
What I could do, my third loop could be this.
The full one.
The full one.
Yes.
And that's okay.
That's okay.
Right? There needs to be some overlap. There can be some overlap, but there needs to be some independent variables also. For example, I could also do this. This could be my first loop.
Yes.
My second loop could be this. That is what we did just now. And my third loop could actually be this.
Entire thing.
So this voltage source is common to all 3 loops.
Yes.
But it's not a problem because every time I'm having some independent currents and voltages.
Exactly. Right. So effectively you're saying now I1 R1 will be equal to I2 R2 equal to I3 R3, which is all equal to VDC.
That is
right?
correct. That is correct.
And hence it's just 1 by R equivalent will be 1 by R1 plus 1 by R2 plus 1
That's
by
absolutely
R3.
right. So if you combine these 3 equations, you will basically get this. So imagine that this is I1, I2 and I3.
Yeah.
I will basically get I1 R1 plus I2 R2.
No, you will get VDC equal to I1 R1 equal to I2 R2.
Oh sorry, equal to I2. Correct. Because they are in parallel.
They are all parallel, right?
Equal to I2 R2 equal to
I3 R3. Right. And then
And then I will use this with the KCL equation.
Yes.
Which is IDC is equal to I1 plus I2 plus I3, because that IDC current is splitting into the 3 parts. I use these 2. We can give this as maybe as an exercise to the reader, to the viewer, but basically you will get something like this: 1 over the inverse of 1 over R1 plus 1 over R2 plus 1 over R3.
Okay.
And now you can extend this. As you can see, the inverse of the equivalent resistance for a bunch of parallel resistances will be the sum of the inverses of the individual resistances.
Excellent. Okay.